Anyway, it's going to be a little bit complicated. I'm going to do my very, very best, though, to give you some strategies and tools to keep everything straight so that when we finally take the test, you'll feel ready. I will also warn you that this test is a long test. I have tried to delete some of the questions, and I just feel like it's going to be better for you if you have more questions worth less points than fewer questions worth a bunch of points. And so what I'm probably going to do for Chapter 5 test is assign you all Encore the day we're testing and let you start the test in Encore. And that way you have a full 2 hours to take the test. Just so that time isn't an issue. You may not need it. You may be done in an hour and a half and be finished. But this won't be next week. This will be like when we're done with the entire Chapter 5 chapter, okay? There's 8 sections, plus we're going to spend 2 days, one doing a little project and one doing a review of radicals. So it's long. And so I tried, and I kept thinking if I could delete this and delete this one, then all of a sudden you've got a very few amount of questions worth a lot of points. And I just don't think that's going to make you the most successful, okay? So be prepared for that when that's coming, that day you won't have Encore to study for your test because I'll have you come in and start the test, okay? All right, that's not next week. We are not testing next week. Okay, moving on. Here we go. So, a couple words. Locus, we're not going to focus on too much, so don't stress about locus. It will not be on your vocab test, so you can cross it out. It's not on your paper. You can make a note to yourself, locus is not on our vocab test. Equidistant is on your vocab test. When they tell you that a point is equidistant from something, first of all, I would point out there is no L there. It is not equal. It is equidistant. But when a point is equidistant from 2 objects, that just means it's the same distance from those objects. So if I said I am equidistant to Edwin and Katrina, the distance from me to both of them would be the same. Okay? So keep that in mind when you see that word in a problem. Okay, so this whole section is mainly 2 theorems and their converses. That's what 5.1 is all about. The perpendicular bisector theorem and then the angle bisector theorem. Huge. I will tell you though, these problems are not hard on the test, and then because it's the first lesson we learned and the test is going to be a week and a half away, a lot of times students forget about these. So make sure that you go back and study these theorems. Perpendicular bisector theorem says if a point is on the perpendicular bisector of a segment. So first of all, look at your segment AB. What is the perpendicular bisector in this picture? XY or line L, right? Same thing, XY or line L. It is a perpendicular bisector. That means that it's forming a right angle and it's splitting the line segment into 2 congruent parts. This says if you have a point on that perpendicular bisector, then that point will be equidistant to the endpoints. So the distance from X to A and the distance from X to B will be the same. And it could be any point anywhere on that perpendicular bisector. So if I had a point right here, it would be equidistant to A and B. Not necessarily the same distance, but those distances would be equal.
What does it say, like, A line, B line off the grid?
Then that means that can't be the perpendicular bisector.
Oh, yeah,
Okay, so if it's the perpendicular bisector of the segment, any point on that line will now be equidistant to the endpoints of the line segment. Does that make sense? Everybody with me? Okay, so the converse is going to say, if you look at a picture and the distance from a point to the endpoints is the same. So now we're just going backwards. If the distance from X to A and X to B is equal, then you can conclude that this line XY must be the perpendicular bisector, which means you can say it's perpendicular and it's splitting that line segment into 2 congruent parts. Okay, so they're just converses of each other. Perpendicular bisector, they give you that it is a perpendicular bisector. The converse, they don't tell you it's a perpendicular bisector. Yep. So this one, they don't tell you it is. That's what you're concluding. Is everybody clear on the 2? All right. So then we look at a problem, and then these start out to be super easy as long as you understand the theorem. So like I said, the questions on the test won't be hard as long as you remember the theorem. Then the math is easy. It says find each measure. They want you to find TU. So look at the picture. Do we have a perpendicular bisector? What line is the perpendicular bisector? UW. Yes. UW is the perpendicular bisector because it's forming a right angle and it's bisecting the line segment, TV. So that means what about TU and VU? They're congruent. Okay, and so then we just set them equal. 3x plus 9 equals 7x minus 17. And the math then becomes super easy. Just don't make little mistakes. Be careful. By the way, this will be our last chapter test that you do not get a calculator for. After this chapter, we start second 9 weeks, then we will get calculators, okay? From here, what would we do to solve? Add 17 to both sides. So we have 3x plus 26 equals 7x. Subtract 3x. And 26 equals 4x. Divide by 4. What do we get for x? 6.5. Because 6 times 4 is 24, and then we have 2 out of 4 left over. So 6.5 or 6.5. And then it says find TU, so we need to plug it in. So we come over here and do 3 times 6.5 plus 9. What's 3 times 6.5? 19.5. And 19.5 plus 9 is 28.5. Oops, I don't know why I wrote that twice. 28.5. Remember, do not put a line segment above TU. Not when you're giving me the distance. Any questions? Was this the perpendicular bisector theorem or was this the converse? They gave you that it was a perpendicular bisector, so it was the perpendicular bisector theorem. If they give you it's a perpendicular bisector, it is that theorem. If you're concluding that it's a perpendicular bisector, it's the converse. Okay, next one. Given the line L is the perpendicular bisector of DE, and EG is 14.6. Find DG. And I promise you'll have questions even like this on your test. Super easy. So line L is the perpendicular bisector. So that means you know that DF is also congruent to EF, right? But what you're using is the perpendicular bisector theorem to say that means GE is now congruent to DG, right? So what is DG? 14.6. Don't put a line segment above it, and you should have easy answers there. Right? Are we good? Super simple? Okay. It's just got to stick for a couple weeks, though. All right. So moving on here. It says, remember that the distance between a point and a line is the length of the perpendicular segment from the point to the line. In other words, if I have a line and I have a point and they say the distance from P to line L is 3. You need to know that what they're saying is the shortest distance. So that's always the perpendicular distance. Okay? So if they say the distance, they're talking about the shortest possible distance, which will always create a perpendicular line. Does that make sense? Okay, because I wouldn't measure my distance from me to the wall by walking diagonally. I would measure it straight perpendicular. Okay? All right, so second theorem. We've learned the first one, now we're learning the second one. The second one is the angle bisector theorem. The angle bisector theorem, again, starts with an angle and it has a bisector. So it says if you have a point on the bisector of an angle, what's my angle bisector here? Ray PC. This ray is splitting the big angle into two congruent parts, right? Okay, if there's a point on that ray, this theorem says that point will be equidistant from the sides of the angle. Here's the kicker though. You can't draw the distance from that point to the side any way you want. That's what I was just talking about. When they say that point C is equidistant to the sides, they have to be drawn perpendicularly. So now these two distances are the same, CA and CB. They'll try to trick you. They'll do this. So angle bisector, agreed? Have a point on the angle bisector. Should be equidistant to the sides. Is x 7? We don't know. It could be, but we don't know for sure that it is. Why not? Doesn't have a right angle box. It's got to show you that these are drawn equidistant by going perpendicular. So you would say, we can't, not enough information, or no, but you would definitely not say yes, okay? Because you don't know that for sure. Okay, so be careful. This has to be a right angle box for you to conclude that these are the same. And if that's a right angle box, then yes, this is 7. Okay, so angle bisector theorem says if you have a point on the angle bisector, it is equidistant to the sides. Just make sure that the distance is drawn perpendicularly. And then the converse is just going to go backwards and say, if you have a picture but you don't know that the angle's been bisected, they don't tell you it's an angle bisector, there's no markings to indicate it, but you notice that there's a point that is equidistant to both sides. Right angle boxes, congruent marks. You can say then that PC is an angle bisector, therefore this angle is congruent to this angle. That's the converse. And again, the way I remember which one's the theorem and which one's the converse is the theorems give you the name. They give you that it's an angle bisector. They give you that it's a perpendicular bisector. Okay, the converse is trying to conclude that they are. Any questions? Okay, look at an example. Again, they should be easy math. It's just understanding the theorem. So you look at the picture. Do they tell us that we have an angle bisector? No. What do they tell us? Okay, so they show us that this distance ML and MJ is congruent, right? And the converse of the angle bisector theorem said if those distances are the same, then what must be true? And what is an angle bisector in this picture? KM. So it's saying that KM must be an angle bisector. And if it's an angle bisector, what does that mean about 3A plus 20 and 2A plus 26? They're equal. So 3A plus 20 equals 2A plus 26. And I know I'm spending a lot of time on words, but I'm trying to make sure if you have to explain something that you understand how to explain that. So those distances were congruent. Therefore, it is an angle bisector. And now these angles are congruent. So just subtract 2A and subtract 20. So what is A? 6. And then what did it ask you to find? Measure of angle MKL. So that means we're looking for this angle right here. So 2 times 6 plus 26 is 38. And what's our units? Degrees. And again, don't forget to put those little M's when you're giving me the measure of the angle. Any questions? I did that pretty fast, so tell me if I've lost you anywhere. Okay. So next problem. Again, should be easy. Just be careful with your picture. Given that YW bisects angle XYZ. So YW bisects angle XYZ. That means that we should be able to mark this angle congruent to this angle, right? Okay. And it says WZ is 3.05. And the question is, what is WX? Good. Again, they are drawn with little right angles, so we do know that because it's an angle bisector, those distances should be equal. So it is super simple. We just say WX equals 3.05. Was this the angle bisector theorem or the converse? Good, angle bisector theorem, because they told you you had an angle bisector. Okay? All right. I think we have two more, right? Okay. So let's look at this one. You guys take a moment to read it, and I'm going to pass out a sheet of graph paper for the last one. No, I couldn't have done that again if I'd have tried. I grabbed the exact number of pieces of paper without. That's the only talent I've had today, let me tell you. All right, so let's check and see how you did. S is equidistant from each pair of suspension lines. S is equidistant from each pair of suspension lines. The suspension lines are our PQ and RQ. Those are the things going down from the parachute, right? So it's equidistant to those. Be careful. Is that saying that SP is congruent to SR? No, because remember that when you draw your distances, if it's saying equidistant, that has to be drawn perpendicularly. So it's saying these distances are equal. Okay? So be careful there. What can you conclude about ray QS? What is ray QS then? It bisects what? Angle PQR. So QS is an angle bisector of angle PQR. Does that make sense? That one was a little tricky because a lot of times students want to think that means SP and SR are congruent. But when you think about the distance from a point to a line, it has to be drawn perpendicularly. Okay? Last one's probably the hardest one of this section. And so that's why I gave you a piece of graph paper. I'm going to try to do it up here on the board so that Tyler, Caden, and Alexis can follow along. I normally do it under the dot cam with graph paper, so this may not be the perfect little graph. Bear with me. Go ahead and graph these 2 points on your graph paper. So we're going to graph 10, 1, and 6, -5. And then connect your dots to draw your line segment. Okay, so it says write an equation in point slope form. Let's stop right there. Remind me from chapter 3, what is point slope form? All right, so we got good point slope form. So write an equation in point slope form for the perpendicular bisector of the segment with these endpoints. Is it asking you to write the equation for this segment? No. It wants the equation for the perpendicular bisector. So we're having to write an equation of a line that's going to go through this segment. When it goes through this segment, if it's perpendicular, what's it going to form? Good and good. It's going to form a right angle, but it's going to have the opposite reciprocal slope. So first of all, that word perpendicular means we're going to need the opposite reciprocal slope. Okay? So we're going to need to figure out what is the slope of CD, but we want ours to have the opposite reciprocal slope. Very good, Katrina and Edwin. And if it's a perpendicular bisector, where does that mean my line's going to cross CD? Okay, and what do we call the point that's directly in the middle? The midpoint. So the second thing we're going to need to figure out is what is the midpoint of CD? Yes, we would. Okay, so to write our equation, we need to know the slope, which we just said it should have the opposite reciprocal slope. And then since it's point slope form, we just need a point. We don't need a specific point. So as soon as we find the midpoint, we'll have a point on our line. We can plug that into our equation. So that's all you have to do. Okay? But it's longer because it's several steps. So let's start with number 1, finding the opposite reciprocal slope. So what is the slope, first of all, of CD? So we're going up how far? Okay, because we're going up 6 and we're going over 4, and then that reduces to 3 over 2. Just counting rise over run. Is everybody with us if we go from C to D? Or you could have went down and left, which would have made them both negative, which still gives us a positive 3/2. So what is our opposite reciprocal slope then? Negative 2/3. Okay, so we have that value. We'll plug that into our equation in a moment. And then we know we want it to be the perpendicular bisector, so we need to know where is the midpoint for it to cross. So to find the midpoint of CD, you remember your midpoint formula? X plus X. Remember, you average your X's, average your Y's. So we will have what plus what? 6 plus 10 divided by 2, and then we'll have negative 5 plus 1 divided by 2. Is everybody with Katrina using our coordinates here? Okay, so what do we get when we simplify that? So 16 over 2 is 8, comma, yes, I'm sorry, careful me, not careful you, perfect. Yes, negative 4 over 2 is negative 2. Remember, these are not your answers. Your final answer is supposed to be the equation in point slope form, so all you have to do is substitute in your slope, substitute in your x1, and substitute in your y1, and then you'll be done. So the equation of our line should be, good, y plus 2 equals negative 2 over 3, parentheses, careful, x minus 8. And this is the equation of the line. You could graph it if you wanted to make sure that your line actually crosses through the midpoint and looks to be perpendicular. But that's it, 5-1.
When you give them that, it's fine.
Mhm. That's exactly true. I would agree. I would agree. All right, so everybody feeling somewhat confident with 5-1? Okay, 2 theorems, and that's really it, but being able to apply the idea of a perpendicular bisector to Algebra 1 graphing and writing equations. 5-2. This is where we start applying these concepts to triangles, okay? And when we do this, we're going to end up learning what are called points of concurrency. And we're going to learn 4 points of concurrency before we're done. Hopefully 2 today and 2 on Monday. When you learn those 4 points of concurrency, you've got to keep them straight. Which one creates what, and what is the theorem about it? And that's the hardest part of this first 4 sections. So I made up a little acronym when I first started teaching geometry because I had never learned this in high school, and then I had to learn how to teach it, and I had to make sure I was competent teaching it and I could remember it. So one thing that helped me was to have a little acronym, and so I'll teach that to you. If it helps you, use it. If it doesn't, don't. But it's just something I came up with to keep them straight for me. All right, so vocabulary, a little more vocab this time. We're going to talk about what does it mean for lines to be concurrent, what is a point of concurrency, and then again, you're going to learn 4 of them. One of those points of concurrency is called the circumcenter. The other one is called the incenter. We're going to learn what does it mean to be circumscribed and inscribed. Okay? So we'll learn those words. So starting with, oops, if we have a triangle has how many sides? 3. So that means in our triangle we could technically create 3 perpendicular bisectors, right? We could do one there, we could do one here, and one straight down, right? And it might go through the vertex, it might not. It just depends on what kind of triangle you have. But we could create 3 perpendicular bisectors. So that's what we're going to look at today, is what happens when we apply this idea of a perpendicular bisector of an angle to, or of a segment, sorry, perpendicular bisector of a segment to 3 segments on a triangle. Okay? And we're going to look at what happens and where they intersect and what does that mean. And then we're going to do the same thing to the angles. So we're going to take the idea of an angle bisector and we're going to draw in all 3 angle bisectors. And we're going to see what happens. But that's the big idea. All right. And again, I just said this, it might pass through the vertex, but I do want to be clear. The perpendicular bisector of a triangle does not have to go through the vertex. For example, if this is the midpoint and I draw the line that is perpendicular through that midpoint, notice it does not go through the vertex. If it's an equilateral, equiangular triangle, then it's going to go through the vertex. But if it's not, it won't. Okay? Unless it's isosceles, that would too. Okay, so just be careful. Perpendicular bisector does not always pass through the opposite vertex. It can, but it does not have to. It has to be perpendicular and it has to bisect. Okay, so here's our first one. So first of all, when they talk about the word concurrent, what they mean is 3 or more lines intersecting at one point. 1 point. These are not concurrent lines. They do not intersect at 1 point. These are concurrent lines. They intersect at 1 point. Okay, so concurrent just means 3 lines intersecting at one common point. If you think about the corner of the ceiling over here, we have a line from this, a line here, and a line going up, and they all intersect at 1 point. They're considered concurrent. When 3 lines are concurrent, they create what's called a point of concurrency. So this point right here is our point of concurrency. It's the point where the lines meet. So the point where they intersect. And we're going to learn 4 different points of concurrency that are created by drawing in 4 different kinds of objects. 2 of them today are when you draw in the perpendicular bisectors and when you draw in the angle bisectors. 2 on Monday will be 2 different ones. Okay? So it says in the construction you saw. You did not see in a construction because I did not take the time this morning in the warm-up to have you do the constructions. We could have. We're not going to. This is the best that you got, which was my hand-drawn quick little sketch up here. Here's some perpendicular bisectors, here's some angle bisectors, okay? What they want you to see, if we had done the construction, is that if you had drawn these in perfectly, pretend I did, they will all intersect at one common point. And I don't know if you remember, and I don't know if we even did it in this class, but we definitely did a core math page before the chapter 1 test when we learned how to do the angle bisectors with constructions. Do you guys remember we got out a core math page and we practiced some harder problems, and one of them was a picture of a triangle and we had to draw in the angle bisector of one of those angles? We could have done all 3. I don't remember if we did all 3 in here, if we just did 1. Okay. If we had done all 3, it was leading up to this lesson today. And there was a question under it that asked you what happens when you draw in all 3 angle bisectors, and we probably didn't discuss that question because we were doing it today. And that's where this is going to occur. So if you had drawn in all 3 perpendicular bisectors correctly, they would intersect at 1 point. If you draw in all 3 angle bisectors correctly, they will intersect at 1 point. And that means they're going to be concurrent, which means they're going to create a point of concurrency. Are you guys with me? Okay, and you're just going to believe me. If you don't believe me, get a compass, go home, and practice drawing those in, and you'll see that they really do intersect at one point. Okay, so the first point of concurrency we're going to learn today is called the circumcenter. The circumcenter is the point of concurrency of the perpendicular bisectors. It's the point of concurrency of the perpendicular bisectors. So where these meet, this point is called the circumcenter. Okay, and that's by drawing in the perpendicular bisectors. All right, and each one of these points is going to have a theorem that's associated with it. And the theorem is the name of the point, so it won't be hard to remember the name of the theorem. Circumcenter theorem, here's what it says. And this is where it can get a little tricky. The circumcenter theorem says if you draw in the perpendicular bisectors, so first of all, look at this picture. What color of lines are the perpendicular bisectors? The red. The red ones are showing to be perpendicular and they're bisecting the sides of the triangle. Do you guys agree? So the red lines are our perpendicular bisectors. Okay? So what they're going to tell you is if you take the circumcenter and you connect it to the vertices, so that would be the blue lines. Go from P, the circumcenter. This is the circumcenter. If you go back from the circumcenter and go to each vertex, they will be equidistant. The distance from P to B, P to C, and P to A will all be the same. We good? Okay, so up here in my picture, just to try to make this make more sense, I found my circumcenter by drawing in my perpendicular bisectors. If I connect this back to the vertices, then all of those distances are the same. Are we clear? So here's how I remember it. If I'm drawing the lines through the sides, the perpendicular bisectors, then the point's not going to be equidistant to the sides, it's going to be equidistant to the angles. So from here to each angle will be the same. That's the circumcenter theorem. Okay. For those of you who hate the always, sometimes, never questions, I'm going to give you a hint that right now what we're getting ready to talk about will be the always, sometimes, never questions you're going to see on your next test. Okay, so it says the circumcenter can either be inside the triangle, outside the triangle, or on the triangle. And then they have drawn them for you. You're going to need to know where is the circumcenter. Is it inside, outside, or on? And for what kind of triangle, where does it land? So first of all, if you want to help make this really connect, again, remind yourself that the red lines here are the what? What did they draw here? Perpendicular bisectors. And yours aren't color coded on your paper, so you may want to go and draw in perpendicular bisector. Perpendicular to the side, bisecting the side. Perpendicular, bisecting the side. And do that on each picture. So it's perpendicular, bisecting the side. Perpendicular and bisecting the side. Perpendicular, bisecting the side. I'm taking the time to do it in case you want to, so that I'm going slow enough for you to do it. Perpendicular, bisect. Perpendicular, bisect. It's bisecting the sides of the triangle, right? So then the point, what's the point called again where they meet? Okay. The point of concurrency is the general term, but circumcenter is what we're looking for because it's specific to the perpendicular bisectors. So each of these points that you see in the picture are the circumcenters. So that's the circumcenter, here's the circumcenter, and then over here we have our circumcenter. Okay, so where is the circumcenter always going to be if it's acute? Inside the triangle. Where is the circumcenter going to always be if it's obtuse? Outside. Where is it going to be if it is right? On. So I may say a question like, the circumcenter is always, sometimes, or never inside an acute triangle. Always. Okay, those are going to be things that you will see the always, sometimes, never questions about. And I will give you a little trick on how it'll be easier to keep track of which one's what later. Okay? Any questions so far? Okay, and again, what we learned is this is equidistant to the vertices, okay, or the angles. You're going through the sides to make it so it's equidistant to the vertices or the angles. All right, the next word we need to talk about is circumscribed, and then I'll explain why they're showing you this. If they say that a circle contains all the vertices of a polygon, then that means the circle is circumscribed about the polygon. If your polygon's vertices touch the circle so that the polygon is inside the circle, then the circle itself is circumscribed. The circle is circumscribed if the polygon is inside of it touching all the vertices. Correct. So circumscribed circles are circles that can be drawn touching every vertex of your shape. Okay? All right, so think about that. If P is the center of the circumscribed circle, and P is also our circumcenter of our triangle, what is this distance called in the circle? What is it? It's the radius. And what do we know about all radii in a circle? They're congruent to each other. So what we just learned was the circumcenter is equidistant to the vertices, and the reason that's true is because that distance is the radius if you draw the circumscribed circle around the polygon. So these will all be the same because the circumscribed circle, that distance is the radius of that circle. Does that make sense? Okay, so keep in mind circumscribed means the circle is on the outside of your polygon touching your vertices. Okay, and then we have these crazy pictures, and this is where it gets a little more complicated. We've got to apply these theorems to a picture and solve for missing parts. Best advice I can give you, draw the picture, mark the picture with all of the information that you know and or given before you try to make your decision, because then it's super easy after that. So what do we know about DG, EG, and FG? They're perpendicular bisectors. So DG, they already showed you that it's perpendicular, but it means it's also a bisector. So it's bisecting the side of the triangle. Mark it. Same thing for EG. EG is perpendicular, and it's bisecting the side of the triangle. Mark it. And you may think, I don't need to do that right now, but when you get to the test, it's a great strategy to help make sure it makes sense. FG, perpendicular, bisector, mark the side of the triangle, showing that it's been bisected. Which means, where do those blue lines intersect? At G, and that is the circumcenter. And what did we learn about the circumcenter? It's equidistant to where, Sarah? The vertices. Vertices are angles, whatever you want to say. Vertices is the point, which is really what it's equidistant to. So we know that GB, GC, and GA are all the same, right? That was the circumcenter theorem. So I've got everything marked now, so to answer this question should be really easy. It says find GC. So GC is the same as GB, which is 13.4. So the math is really easy once you have your picture marked with what you know. But you have to know the theorem and to know what you can mark, right? Questions? Okay. And it won't seem too bad right this minute because it's the only thing we've learned. When we learn 3 more and you've got to put them all together, that's when it gets a little bit crazier. Okay, again, let's mark our picture. It says use the diagram, find GK. KZ is a perpendicular bisector of triangle GHJ. So K, you don't have this sentence? You would have to have that to do this problem. Write that down. So sorry, I should not have cut that out of your notes. Okay, let's take that KZ is a perpendicular bisector and mark your picture. KZ is the perpendicular bisector. Remember, it's of the side of the triangle. So that means that this should make a right angle, and it should bisect this side of the triangle, right? You guys with me? Okay. And they want me to find GK, which is this piece, which means it should be equal to what? KH, which is 18.6. So it's super easy math. But you have to know the theorems or it won't make any sense. You have to know the definitions. What's it mean to be a perpendicular bisector? Okay? Same question, same information, but this time they want us to find JZ, not the wrapper. Okay? I don't know why it just did that. Oh, good grief, Ashley. There we go. Okay, so let's go back and mark what we already knew really quickly. KZ was the perpendicular bisector. So I'm going to go back and put that on my picture. We're looking for JZ. What do we know about all the perpendicular bisectors in this picture then? Or at least two of them. What other one would have to be a perpendicular bisector? LZ, what else? ZM. Because we know that this is a perpendicular bisector, so where they touch there at point Z, that point Z is now going to be our circumcenter. Okay? So what do we know about the circumcenter and the distance to each vertex? They're congruent. So JZ should be the same as GZ and HZ. Okay? So what is JZ? 19.9. Are you following me? Questions? Okay, let's look at the hardest one and we'll stop with it today. And that means that you need to do, I'm telling you guys, because it's going to be intense next week if you don't, you need to do all of the first page of the homework, all of 5.1. You need to do every problem that's about circumcenters on the homework on 5.2, but we won't get to the incenter, which is the second one. So anything that's about an incenter, don't worry about it, save it for Monday, okay? But let's go ahead and see if we can do this problem. So get back out that graph paper. And you may want to make a note that this is going with section 5.2 notes or 5.1 notes so that you can put your graph paper with your notes. Because oftentimes you go back to study and then you don't have your graph paper, you don't know where it went. So put it together. Make a graph. Let's graph this triangle. 0, 0. 10, 0. And 0, 6. I already gave it to you? Oh, I'm sorry. I didn't know you guys had a graph already. So you can use yours. It may be too small, so feel free to draw a bigger one on your graph paper. Okay, they want us to find the circumcenter. So remember, what types of lines do we draw on our triangle to find where they intersect to create the circumcenter? Perpendicular bisector. So if they say find the circumcenter, you have to know when you get to the test that that means you need to draw in perpendicular bisectors. And you're looking for where they intersect because those lines are concurrent and the point of concurrency is the circumcenter. Does that make sense? Okay, so we have three sides of our triangle. We could draw in all three perpendicular bisectors, but how many do we need to find out where they intersect? Just two. As soon as two of my lines intersect, I'm going to know where the circumcenter is. So you don't have to draw all three. You could just draw two, but you have to draw at least two. Okay? So let's do the two easy ones first, and then we'll talk about the third one if we have time. So KH would be easy because it is vertical. To find the midpoint of KH would be easy, and then to find what type of line would be perpendicular would be easy. We want the perpendicular bisector of this. What's the total distance? So what's the halfway point? 3. So we know it's going to pass through the midpoint. And we want it to have the opposite reciprocal slope. So since this is vertical, what kind of line should it be? Horizontal. So we're just going to draw this little horizontal line. And then what would be the other easy side? Okay, the HJ side, because it's horizontal, it's a length of 10, so what's the midpoint? 5. And then since it's horizontal, what kind of line would be perpendicular? Vertical. So we're going to draw a line through there vertically. And yours will be more precise than mine. I wasn't too bad. Here. We'll talk about that in just one second. So do you guys see where these cross? What are the coordinates of your circumcenter? Said find the circumcenter. So the circumcenter is at what coordinate? 5, 3. Now, before we look at the third one, I want you to think back to what we said about where the circumcenter lands. What kind of triangle do we have here? It's a right triangle. And we said if it's a right triangle, where is the circumcenter always going to be? On. And it's going to be on the hypotenuse every time. Okay? So this just reinforces that. If it was not vertical and horizontal and you were having to draw in the perpendicular bisectors, then you would have to find the midpoint. So let's do that with KJ just to practice. So if I want to find the midpoint of K and J, it would be, very good, careful Tim, plus 0 over 2 and 0 plus 6 over 2. What does that reduce to? 5, 3. Okay, but again, make sure you understand that because you'll have some on your homework that aren't right triangles, and so you don't have a vertical and a horizontal. So you have to do the diagonal. So we know we're going to have a point that the line's going to go through this point, which it should because we just said that's the circumcenter, right? And then how do we figure out where to draw that line? The opposite reciprocal slope. So what's the slope of KJ first? Down 6, right 10, which reduces to? Negative 3 over 5. So we want the perpendicular slope. So what's the opposite reciprocal? Positive 5 over 3. So then what we would do from this point is go either up 5, right 3, or down 5, left 3 to graph that line. So let me draw in some more points here. So I would go down 5 and then left 3. And then I could draw in that line for my perpendicular bisector. So be careful. If they're not nice and easy vertical and horizontal, think, okay, I've got to find the midpoint and I have to find the opposite reciprocal slope, graph the line, do it again until you find where they cross. Any questions on circumcenter of a triangle? Okay, so Monday,